Good afternoon, all, and welcome to the presentation of the project. Our project, before we kick off, and I'd like to just introduce the team. My name's Gavin Heron. I'm the Operations Director of Trotec. We've got Storm Wilson, who's the Senior Project Manager that ran this contract, and Dylan Titus, who is the Engineering Manager of Trotec. And he did all the design and compilation of drawings, etc., and the technical input to it. Right. In essence, the project we undertook was for Botswana Oil. It was a depot that was built to increasing capacity size in Francistown. So as we got the architects were ourselves per se, main contractor was Trotec. We undertook the full design responsibility of the project. The brief was actually very simple. In essence, Botswana Oil's mandate was clear in us securing, managing, and distributing a petroleum product in a way that supports their operational efficiencies and long-term sustainability. Botswana, unfortunately, is landlocked, and there was a strategic decision for them to increase their fuel capacity to have reserves of up to 60 days, thereby strengthening their energy security, which most sub-Saharan African countries are doing. The brief was quite simple in the fact that we had to increase their capacity to a 60,000 cube depot, which consisted of 4 tanks. Each tank had a capacity of 15,000 cubes. The dimensions of the tanks were 30 meters and a height of 23.5 meters. And we'll get into more of the technical details as we go through the presentation. So if we go to the next slide there. Sorry. We're sitting, one's in Durban, one's in Joburg, one's in Cape Town. So just an overview of the vision that we try to achieve when we undertake these projects as well, from a structural performance point of view, to provide enough strength to safely contain petroleum products under operational conditions and obviously environmental conditions with wind loads, etc. It's also to optimize our shell design through variable plate thicknesses and the high strength to weight ratio, which allowed efficiency tank geometry, which is the tank geometry itself. The durability and life cycle performance compatible with advanced blasting and coating systems. That's through experience of coating with petrochemical products, ensuring a long-term corrosion protection and reducing maintenance requirements over the asset lifetime. The integration and functionality, we looked at certain aspects of the contract, and we brought in aluminium geodesic domes, and you'll see in the technical presentation the reasoning for that decision. We've also utilized internal floating roofs, and once again you'll see that further on as well, so I'm not going to harp on those subjects. Nozzle access systems and firefighting infrastructure were all part of the integration into the tank build itself. The project-wide application of steel, obviously steel was utilized across most of the project. It included obviously the main structure, which is the floor and the shell components, the site establishment, containers, awnings. Our complete site establishment was built of steel as well. All our erection aids and temporary works would consist of steel, and the full scaffolding system for access and construction. So a large component was built around steel itself. The project overview, we completed this project at the beginning of November, the end of October, November. That was our contractual completion date. The total cost of the project ended up just over 300 million rand. The type of structure was above ground storage tanks, otherwise commonly known in the industry as AST. which is self-explanatory, and then features of the structure for export and the Pan-African market, obviously being a cross-border project. The sector we've put across is for infrastructure itself. Now, we've given a high-level project overview. I'm not going to spend a lot of time on this because a lot of the challenges and the technical input will fall out in the presentations as we go along by the rest of the team. I think I've explained the reason for the strategic expansion was to increase the capacity and secure fuel storage for Botswana itself to 60 days. So I don't think we need to go into any more detail than that. Obviously, the project intent has been explained, the key challenges. Once again, that will be addressed as we go along because a separate section that covers this. So I don't want to steal anyone else's thunder on that as well. The technical construction motivation, innovation. I think Dylan will cover that quite in depth in his presentation as we talk, and obviously the rest of the considerations as well. So the project overview is also, as we said, the project completion date. The cost of the steel work alone was in the region of 28 million. The tonnage we utilized 1,200 to 1,500 tons of carbon steel plate, which includes our channel, our angle lines, all the nozzles and appurtenance attached to the tank, the profile, and then we obviously had the aluminium side of it, which was about 35 tons, consisting of the 4 geodesic domes and 2 internal floating roofs, which you'll see down the line as well. Profiles used, obviously carbon steel, the floor and the multiple courses for the shell, the structural steel, channels and angle line, roof structures, aluminium and geodesic domes themselves. I'm going to hand over now to Dylan. As I said, Dylan is our design manager, and he'll take you through the structural framing of the contract. Thank you. Dylan?
Yeah, just unmute. Thank you very much, Cap. Yes. Okay, just mute yourself.
I'm sharing the screen here.
Okay.
Mute yourself, you can talk through me.
I'll talk through.
Yeah, there's a bit of an echo there, guys.
Can you hear me now, Gavin?
Yes, that's better.
Better, okay, cool. Sorry about that. Great, okay, I'll talk about the structural framing. So, just an overview of our structure. There were 4 above ground steel storage tanks, diameter 30 meters and height 23.5 meters. Each tank is made of a steel cylinder, which is steel plates which are rolled to get the diameter of the tank. In order to make up the cylinder, you have 10 courses of shell plates, starting with the thickest at the bottom is around 20 millimeters thick, and in progression getting thinner down to around 8 millimeters at the top. The floor is also steel, that's a steel flat plate. So just to touch on that, the thickness changes. So that is just an example of the efficiency of steel, where we can use just the material that we need and not make the entire shell one thickness. Each shell is topped by aluminium geodesic dome roofs. As Gary mentioned earlier, that was the aluminium part, and we also have an aluminium internal floating roof. Okay, then we also have a top wing girder and a walkway. Sorry, a top wing girder which doubles as a walkway, and this is stiffening the shell around its circumference.
Dylan, is there any chance you can speak up a touch or just get the mic a touch closer to you?
Closer.
Sorry about that, guys.
No worries.
Is that better, Gavin?
That's fine. That's much better.
Okay, cool. So to continue how the project illustrates the benefits of steel. So welded steel safely contains large volumes of fuel while remaining stable in the wind load. High structural efficiency and weldability are key benefits of using steel. Thickness was matched to demand. Thickness was matched to demand of the product. So, as I mentioned earlier, you have a thicker shell at the bottom and a thinner shell at the top, and it gets progressively thinner as you go up. Steel's fabrication flexibility allows shell and wing girder designs to be refined mid-project, improving buildability and reducing site welding. Then to talk about the load path. So when the tanks are full with product, it's mainly under hydrostatic loading, which causes hoop stress in the shell plates. And then when you empty the tank, the main load on there is then wind loading, which can cause buckling or sliding of the tank if not designed correctly. The bracing system, the top wind girder and walkway provides circumferential stiffening of the shell. During the erection, a temporary stiffener was used, which was then replaced by a permanent stiffener or wind girder when it suited the processes on site. Column fixity, okay, that's not applicable to tanks because of the inherent strength of the cylindrical structure. It does not require any columns whatsoever. Overall stability strategy. Stability is carried by the welded cylindrical structure, stiffened around the circumference of the top wind girder. We also have a jacking system, which is used during construction. Also provides a lot of stability for the tank, and using that jacking system, a lot of welding and construction activities can take place at ground level, which is a lot more stable than working at heights on scaffolding and so on. The temporary curb angle stiffener ring controlled windows under the permanent until the permanent girder took over, and then also for each tank, 32 anchor bolts were installed to stabilize the tank under wind loading. What is most notable technically? Wind girders are normally made of continuous rings of plate to facilitate construction and allow improved coverage of firefighting water onto the tanks. The wind girders were designed using structural members instead. This is unique in tank construction. Optimization in design reduced the initial client requirement for 3 stiffening rings. So here it was actually a proposal by the client to use 3 rings, but we redesigned it to use only 1 stiffening ring. And it was quite a good optimization, which saved cost and time on site. Where were the non-everyday design challenges? Yes, we designed a unique wind girder system, and we used finite element analysis to verify the stability of the tank under wind loading. How was efficiency achieved? So tank shell plate thicknesses were reduced to minimum allowable thicknesses to save on cost, time and weight while maintaining structural integrity. Engineering calculations were used to verify the optimization and structural integrity. How were complex connections designed and executed? Bridge to tank joints were designed to accommodate differential movement while maintaining secure attachment to the shell. This allowed so we did that by fixing one end of the bridge and allowing the bridges to slide at the other end, and that allowed for the flexibility required, but also provided the necessary structural stability. Okay, then also nozzle joints to the tanks. These were designed using thickened insert plates, which also required post-weld heat treatment to withstand operational loads. The thickened plates were carefully machined to match the shell thickness seamlessly, and these dimensions of the plates and the machine edges were carefully calculated to ensure structural integrity in terms of, or in accordance with API 653 standard. How was constructability considered during design? So 3D and 4D model representations were developed to assist in constructability decisions. Shell and floor plates were designed and configured to minimize the amount of courses, reducing horizontal and vertical weld seams, which is a huge saving on construction activities. Structural items were designed and constructed to suit transportation and site constraints. Wind girder joints were made from welded to bolted, were changed from welded to bolted to make site assembly easier. And also due to wind girder size, it would have hampered shelf installation on site. We therefore used a temporary girder which was smaller and then installed the actual full-size girder at a more suitable time. Okay, then we just got an image there of the elevation of the tank on the left-hand side and the plan view showing the wind girder on the right-hand side. So it shows some nice details there. You can see the different shell course thicknesses starting at 20 millimeters at the bottom, and then you've got 18, 16, 14, all the way to the top, which stops at 8 millimeters. You've got overall height of the tank there, 23.5 meters. The diameter of the tank, 30 meters. And you can see quite a number of attachments on the tanks as well. And on the right-hand side, where you see the plan view of the wind girder, you can see all the structural elements which make up the girder. Okay, then we've got 3D image on the right, on the left. That's what we used as, that's what we generated as our 3D model of the tanks, showing all the attachments and tanks as they were installed on site. So you can see the location of the tanks, the spiral stairs, the geodesic dome roofs, and on the right-hand side is an example of the finite element analysis that was done on the tank to verify that the unique wind girder structure that we designed actually works and can withstand all the loads that it needs to.
Okay, I can jump in here. So these are some pictures from our fabrication workshop. On the left-hand side here, top left, is showing the shell plates in a roll position. This is after rolling. On the right-hand side, as Dylan and Gavin mentioned, this was a pre-assembly of our wind girder, and this is when we noticed that it would be challenging for our team on site to assemble, and we changed it thereafter to a bolt-on arrangement and a slotted hole arrangement. Okay. On the left, top left, just left-hand side, we can see this picture here shows the floor plates are laid, and we're starting with the external scaffolding. On the right-hand side shows the progress on the external scaffolding as well as the internal scaffolding that's required on the job. On the left-hand side, this is a nice progress picture showing the two tower cranes, your external scaffolding, as well as the cocooning. So if you look at the blue sheeting around the tanks, that's your cocooning to protect the welding against wind. Okay. Another progress picture just shows it's a good picture to demonstrate or to show the stiffening that we've put on the top of the curb angle to prevent the wind from collapsing the shell. And then on the right hand side shows how we progress and jack the tank up, and we fit the strakes in on the underside. Once all the strakes are in and the geodesic dome has been lifted into position, we then brought on the painters, painting contractor MTL, which I think we'll mention later. They then wrap the scaffolding, they erect full scaffold, wrap the scaffolding so that we can cocoon the blasting, the grit, and then they obviously painted. On the right hand side here, this just demonstrates the amount of scaffolding required on the steel scaffolding required on the outside of the tanks, and then shows the finished product on tank 14. Okay.
Right, thank you, Storm. Yes, I'll talk about BIM modeling and software we used. So what innovative engineering solutions or digital tools we used? We used our ANSYS finite element analysis software. We run structural analysis checks on the tanks, make sure everything is working structurally. And then we also use Synchro 4D to compare our baseline program with the actual progress on site, and we'll show you we'll play a video for you and show some images of how it works. Then, how did BIM integration improve problem solving? Early identification of issues such as clash detection between structures or rather different disciplines was able to be done. So that we could do way before we were on site, so we could resolve the issues during planning and design stage before any works were taking place on site. So Storm, will you play that clip?
Yeah, let's just get the clip on quickly. Okay, so I'll just take them through this. So what we're seeing at the moment here on the left-hand side is your baseline. On the right-hand side is your actual progress. On the left-hand side here, you'll see we'll start laying the floor plates. Oh, firstly, the tower cranes, sorry. Once the tower cranes are up, we then put the annulars, we did the floor plates, put the jacking system in. We started with the second last rake, we then put the last rake on top, and then the jacking starts. We jack the tank and we start putting the plates underneath from the bottom up. Okay, I'm going to fast forward because this is obviously a long process. There was 10 strikes. So I'll fast forward to near the end. You can see the wing girders up. We've got the spiral stairs up. And on the left hand side again, it compares your baseline versus your actual. The dome roofs then get installed. Once the dome roofs are installed, we then go on the inside. We paint the floor and then we install the IFR. I think I'm going to end it there. Okay, just hold on. Okay.
Right. So how were flashes identified and resolved? So we generated accurate 3D models of our tanks, and that allowed us to see where all the different attachments on the tank are going, and we could easily identify if any clashes are taking place. And again, this happens long before anything is fabricated or erected on site. So it does provide a big benefit. How did digitalization support design changes? We were able to identify issues prior to fabrication and ensure that modifications to one element don't impact the next. So as I mentioned, now you can pick up a clash and you can quickly just redesign or move things around digitally and find the correct position for them before anything has been done on site. Okay. So here's an example, again, just some screenshots of the 4D model on the left, showing the entire site construction with the schedule, and then the 3D model we generated in Office with showing all the detailed attachments on the tank, all the shell wells, the geodesic roof, and yeah, so we can using that we can choose the correct location for every item and not have any issues on site. Thank you. So we're moving over to metal roofing. I think is that Kevin?
No, that's me. Okay.
Cool.
Thank you, Sullivan. Okay, so on the roof manufacturer, the supplier was manufacturer was HMT, roof former profiler HMT again, and the roof supplier HMT. The roof contractor was us, Trotec. Okay, just on the project overview, the client specified aluminium geodesic domes as well as for all 4 tanks. And then on 2 of the ULP tanks, he specified internal floating roofs. And there's many benefits of the aluminium dome roofs. So obviously it's to deliver high performance, efficient fuel storage. The geodesic dome roof constructed from lightweight aluminium material, which provides self-supporting, and then it's also aluminium is also corrosive resistant. On the internal floating roof side, the floating roof basically sits on the product. It floats as the product is pumped in, it rises with the product, and as the product is pumped out, it is lowered with the product. So it basically reduces your vapor space and minimizes your product losses and emissions while improving operational safety and efficiency. So that's the reason for that. Complexity and difficulty. So this obviously requires high precision. You've got 2 components. You've got the steel tank, and on the and on the outside on the roof, you've got the aluminium dome that obviously needs to be accurate in order to sit on top of the curb angle. Coordination was critical to ensure proper fit up of prefabrication elements, accurate load transfer, and sealing integrity. So on the inside of your floating roof, you've got a minimum distance away from the shell. That is critical in order to not have vapor leaking through the seal. Installation at height, right, introduces safety accesses. That is challenging as well. You've got, once the dome is lifted into position, you've got areas where you need to put panels, and that is a little bit challenging because you're working at heights, top of the dome roof. Okay. So innovation and execution approach. On this project, we normally use the standard system is to use turfers to lift the dome roof. That method you use about 30 guys to lift the roof, and it's time consuming. We instead spec the tower cranes to be able to lift the dome roofs with using the tower cranes, which reduced manual labor, installation time, improved placement accuracy, minimum safety risks associated with working at heights, and then obviously prefabricated modular annual panels allowed for rapid on-site assembly and reduced the rework. Okay, this picture over here on the left-hand side shows you our structure. As the structure is going up, it gets lifted with these tripods over there, and as you lift the tripod, you install another ring. Once we've got enough rings on, we'll start putting the aluminium panels. Okay, this picture on the left-hand side shows us lifting the geodesic dome using the tower crane. On the right-hand side shows the dome roofs in position. You can see there's some panels left out that gets installed once we've actually bolted the roof down to the curb angle and it's all sealed. Okay, this picture just illustrates the aluminium on this dome roof tank. It shows you the aluminium IFR being built on the inside. Okay, moving on to fabrication. The fabrication
Storm,
complexity.
just to be aware, Storm, 5 minutes.
Yes.
5 minutes.
Okay. So I'm just going to have to touch on these things.
That's
So there was
go
some
to the
fabrication.
Yeah.
All right, just go to the pictures, Gav.
Yeah, no, just telling you 5 minutes.
Okay. So quickly, there was 1,500 tons of steel. Just imagine 60 trucks coming to the shop with various thickness of material all mixed on one truck. That is quite complex to handle the material and sort it out. The firefighting system was also quite a challenge to fabricate with different size piping, bolt-ons, screw-ons, weld-on flanges. What made fabrication excellent? Following our company quality management system, accurate plate prefabrication. You can imagine we've got a circumference on the tank. You need to keep the circumference. There's a high level of accuracy. The ease of installation due to prefabricated components being trowel fitted. That was one of the successes on the project. We trowel fitted most of the structural steel in the workshop before we sent it to site. Okay, just quickly, we are ISO 9001 and 3834 accredited. We obviously all components were checked in by our workshop QC as well as Trotec QC to verify before they are sent to site. There was radiographic testing on the site in accordance with API and ASME 9. Okay, there was a mix of bolted sections and welded sections. Just running through this a little bit quick. This picture just shows here the annular plates and well as some of the shell plates in the background, some of our structural steel. This picture demonstrates us just doing our trial assembly. This is our grating, how we trial assemble, then we cut the grating thereafter, making sure that each item fits. On the erection side, the biggest risk that we had was obviously the wind, which could collapse our shell. And we mentioned before how we prevented that using a stiffener. The site flooded. There was a heavy downpour. The site flooded, and we managed that using scaffolding to elevate ourselves out of the water and to provide access for our labor to get to the tanks. There's also a shortage of skilled labor, right? We'll talk about that. Logistics, obviously, it's a cross-border project. Material transport, labor mobilization, and site establishment all added to the complexity. And the way we managed the delivery of material is that we had a minimum of 2 weeks material sitting on site to ensure that there's no stoppages. And I can tell you there was no stoppages on the site due to late material. Minimize disruption in surrounding operations. Work was carried out on a live fuel depot. We had delays. We managed the delays using daily diaries. From managing late stage designs, drawings were always revised and We put a hold on prefabrication, revised the drawings, then sent revised drawings through to the prefabricators, so it was well managed. And we mentioned the shaft thickness reductions. That was a big saving there. But that was also first calculated via design calculations before we made any changes. Sequencing and crane strategy. Yeah, we mentioned this tank was built top down using the jacking system. Tower cranes also position the dome roofs. Okay, these are the progress pictures. Tower cranes up. Tanks. This is the first tray going in. Some pictures showing the stiffening ring on the top. All these white marks here are your NDT, your quality checks that's been done. Okay. Over here, this is your dome roof, your final position. The wing girder going up on the right hand side. Again, dome roof. This just shows the stilling wall going through the dome roof. And then the final painting. Okay. Challenges and solutions, key challenges. Logistical challenges, including material transport. We had all of those. Delays in onboarding skilled labor. We initially allowed for expats to come to site. We only managed to get 50% of that crew through with work permits. So we ended up using 75% of local employees. Cross-border logistics was initially an issue. We mentioned that. We experienced significant flooding. We mentioned that as well. Labor shortages. Okay, this is just a picture showing your truck standing at the border. Okay, the flooding conditions, and we showed how we elevated, we erected scaffolding for elevated platform. Okay, this is just your cooling ring. You can see how detailed the cooling ring is, and the piping that goes around the spiral stairs, and your interconnecting bridges that needs to be precise in order to link up with the wing girders. Okay, benefits of steel. Okay, carbon steel material is for this project was procured locally and it was available. Steel tanks are prefabricated and modular, enable much faster erection versus concrete. So the benefit there is critical for fast track terminals. Structural flexibility. Steel has high tensile strength, ductility, and it's obviously lower leak resistant. Strength to weight ratio. Steel provides high strength at significantly lower weight, reduces foundation loads, lower civil cost footprint, etc. Tight containment. Integration of fittings is easy because you can just cut them through the steel. You don't need to. Constructability and scalability, easy to modify, extend, and repair. So benefits here is better life cycle adaptability versus fixed concrete structures. Leak integrity and maintainability can be inspected, repaired, and patched locally. Right, lower environment and compliance risk. Advantage of steel over alternatives: fabrication flexibility allows shell and wing girder design to refine mid-project, reducing material welding on site. Strength to stand as large self-supporting cylinders. Your life cycle, you can coat the steel, so we use corrosion protection system, which we'll mention quickly. Life cycle economics, while steel may have higher initial material costs, it's faster to build, earlier revenue, lower maintenance and disruption, so better total cost of ownership in the petrochemical application. Quality, quickly, we 9001, 3834, 14001, and 45001. At the start of the project, we develop a PQP. The tank goes under radiographic well testing, right? The reject rate is obviously because we onboarded local labor. We had to train them at the start of the project. So a lot of these failures were right at the start. We had a dedicated QC team. We had 2 QCs from our side. We had 3 NDT technicians and 2 painting QCs. The client provided a third-party inspector on top of what we provided. Hydro testing, once the tanks are erected, we hydro tested them with 15 million liters of water per tank. And then we onboarded skilled welding supervisors with 20 years plus of experience that could actually train and mentor our welders. Inspection procedures, weld joints were visually inspected by qualified controllers. Weld joints are liquid penetrator tested. Tank joints are radiographed. Floor joints were visually inspected. Site painting works was inspected by quality. Then on the painting side, on the external, we use Sigma Zinc 68, Sigma Cover as intermediate, Sigma Cover 350. intermediate code, and then the final was Sigma DIR 550. External services blast to SA 2.5, and then your internal was SA 3. Compliance standards, we obviously compliant with API 650 and the client specification. Tanks were welded in accordance with API 650 and ASME 9. Structural steel items with SANS 10162-1, and then scaffolding SANS 10085. Material optimization, shelf thickness. We mentioned eliminating intermediate wing girders. We mentioned recyclability. So both steel and aluminium are recyclable. Waste reduction, resolving buildability issues. Okay, so and reducing reworks and offcuts. We bolted on the wing girder. We mentioned. Go to maintenance and consideration. Corrosion protection on the steel allows for long service life. Okay. Quality. This just shows you the various inspections signed off by the various QCs and client third parties. On the paint, that's the mechanical, and this is the painting. The painting also went through AIA and client engineer, as well as our QCs. Okay, Gavin, over to you.
Right, guys, sorry, I know time is of the essence here, so what we're proud of. I know we haven't put it here, but what makes me proud about this project is the way the Trotec project team managed themselves, managed the client, and were able to deliver a project successfully. Yeah, success also goes around the safety of the people. We produced in close on 330,000 man hours with 0 lost time incidents, and that's a hell of a feat. If you have a look at the staff that we employed, 75% were local. This is almost a first of a kind in Botswana, the size and the scale that was built, and to produce a safety record with inexperienced people, I think that was a hell of an achievement for us. Like we said, we produced the project on budget and to the highest quality standards. People think that you can go into Africa and produce substandard work. That's not true. We were held accountable for the project, and I believe we delivered on that. One of the standout moments as well, we developed a training school when we saw that there was a shortage of skills, and we facilitated and handed over the training school when we finished the contract, and we had 8 enrollments, 6 graduated, and you'll see down the line the graduation ceremony, and I think we got a lot of praise for that in the Botswana press, that we've left something behind. What makes the project stand out technically? I think from a technical aspect, one of our standouts, although it may seem trivial to a lot of people, was the redesigning of the wind girder. We install wind girders all the time. To redesign and do a bolt-up arrangement that still complied with the code requirements, I think was some very clever engineering, and well done Dylan and Storm for doing that. That saved us an incredible amount of time. Once again, we did the tank jacking erection, never done in Botswana before, so that was a big eye-opener for everyone. And when we also placed the geodesic domes with tower cranes, I think that's also a first. Normally either you use turfers like Storm said, or otherwise you use a normal crane. Exemplary structural and detail elements. Once again, some clever engineering. One of the big risks when you're building a tank is the wind loading, where the instability of the tank as you jack it up. To come up with a double curve angle stiffener that reduced our risk, and also obviously it sets the foundation for a compliant tank from a point of roundness as well. And once again, I'm not going to go on to the bolted cleated wind girders, and that we've spoken about that quite a bit. Beyond technical merit, what makes this a winning project? I'll emphasize the team. That's the first thing, and we delivered within the 14-month program. It was, and when I say it was a tight program, we managed a lot of inclement weather, contractual issues with the client, but there was a lot of transparency, and we completed the project to almost within the hour, not the day, within the hour. So I think the team did an exceptional job there. And obviously a lot of parliamentary guests came in that, and Botswana is renowned for not delivering on big capital projects, and this was one of the first that they've actually done that. So a lasting legacy as well there. Community impact, like I said, local welders and grinders, we trained them and promoted them to boilermakers and foremen. We got involved with the community within Francistown, and we built up a very strong relationship with the town itself, and we supported a few underprivileged sectors within the community, which also went a long way. Like I said, the training school, once we finished, we actually handed that over to Botswana Oil so they can continue the legacy as well. Industry contributions, the capacity once again, that we built locally instead of bringing in the imported labor. Client satisfaction, the project quality, they held us accountable, and you'll see the next slide, the reference letter from the client, the engineer and the clients didn't give us any grace on quality and that, which we appreciated, because then it makes us perform at our peak. Distinctive aspects, this was one of our first cross-border projects, delivered inside a live fuel facility, and we were under the microscope from the mother company, from our management, and obviously the client themselves. And the strong safety and training legacy delivered alongside the infrastructure itself. I think the guys did exceptionally well. The collaboration, there was very good collaboration between the client, the engineer, and the project management team, and I think that goes a long way to the success of the project. When we had labor issues, the client stood with us. They didn't hang us out to dry, and they stood by us, and we worked through it together, and that created a very workable atmosphere as well. The role and coordination in overcoming challenges, as I've said, the guys all working together. We were held accountable for daily tracking and frequent meetings. We had to go up there at least every fortnight, to deliver the project schedules. And I think the success of the project was the openness that we worked together. And you can see on the right-hand side, that's from the principal engineer about the performance. We've taken a snippet out of the letter, and I think you can read that in your own time, to the level that we produced. And here's just a closing slide, and that 2 closing slides was the training school that we built, and the development of the graduation ceremony of the people, and the handover of the certificates. And we're proud of leaving a footprint that changes the landscape and secures the energy future for Botswana. I took a phrase out of one of the politicians: Trotec's success underscores the value of collaboration, innovation, and disciplined execution in shaping the region's energy future. And that's it in a nutshell. Thank you very much, guys. We appreciate it. I know time is tight. Liesl, thank you. And the project team, well done, and thank you once again.